Hello, this is the lecture for section 1.5, transformations of functions. All right, what is a transformation of a function? Well, a transformation of a function is changing it from its toolkit form or parent form into something different. So we call these toolkit functions that we've talked about. What we're going to talk about today is ways to change these functions and what it means to for the graph. All right, there are several transformations that we can apply to a function. Let's start with the vertical shift. If we shift a function vertically, we're either moving the graph of that function up or moving the graph of that function down. All right, we have a definition for that here. If a function is f of x, the new function g of x will be f of x plus k, where k is just some constant. It can be positive or negative. Right? So when we add a value or subtract a value out at the end of a function, we're shifting it either up or down. Okay? If we're adding a positive number here, we're shifting it up. If we're adding a negative number here, we're shifting down. I like to think about it this way. Well, f of x is the output of the function, so the output of this function is getting some value added to it or subtracted from it. So that means all the y coordinates of every point on that graph are either shifting up or shifting down. Let's look at an example. Let's consider... Let's see if I can put this up here. Let's consider, everybody's familiar with the quadratic function from the toolkit functions. That's a f of x equals x squared, looking like that, right? In its most basic form, let's say f of x is equal to x squared. The graph of that is going to look like this. Oops, I'm at that point. That one's off the graph, so it's going to look like this. Okay, that's just f of x equals x squared. Okay, now if I want to shift that up, say I add 2. Let's make a red one. We'll call, actually we'll call him g of x. And that's going to be x squared plus 2. So what we're doing is we're shifting all the y coordinates of every point on this graph up 2, right? Or we're shifting the whole graph up 2. Okay, so that's going to look like this. Okay, and the red one is g of x, which is going to be defined as x squared plus 2. Right, if we were subtracting, I'll grab a different color here, call h of x, call him, let's say x squared minus 2. So what we'll be doing with that is we're just going to take that toolkit function and we're going to shift it down 2 units. So all the y coordinates of all the points on that graph are going to shift down 2 units. And it's going to look like that, like the, whatever color that is, the teal color graph. Okay? All right, let's take a look now at horizontal shifts. With a horizontal shift, what we're doing is we're going to add or subtract some value to the input of the function, right? Or we're going to add or subtract some value to the x. Okay? Now, horizontal shifts can be a little bit confusing because it's sort of counterintuitive, right? If I'm adding a value to the x or to the input, I'm going to be shifting to the left. Intuitively, we want to say, oh, you make the x bigger, you shift to the right. That's not what's going on here. When we add to the input, we're shifting left. When we subtract from the input, we're shifting right. Okay, so let's take a look at an example here. If we look at this toolkit function again, let's stick with x squared quadratic toolkit function. All right, so it's going to look like this in its parent form, or before any transformations are applied to it, as x squared. Now, if we want to shift that to the left, for example, g of x, that's going to be, let's see, x plus 2 squared. I'm adding to the input, so I'm going to be shifting left. It's counterintuitive, but adding here means that we shift left. Okay, so what's this saying? This is saying all the x coordinates of this point are actually going to be increased by 2, but the result on the graph is that it shifts left. So let's see. It's going to look like this. Paint the graph here is g of x, or x plus 2, all of that being squared. Okay, what if we wanted to shift it to the right? Well, let's just say h of x, so the x minus 2 squared, that's going to be, when we subtract from the input, that's going to shift us to the right. Okay, so our green graph, we're going to look like this. Okay, so we've got vertical shifts, shifting up and down. That's going to involve adding or subtracting a constant to the entire function, right? Making the y coordinates change. If we're shifting left to right, we're going to be adding or subtracting a constant to the input, right? Or to the x when we're using x's. Right? And that's going to shift us left to right. It's counterintuitive. When we add, we shift left. When we subtract, we shift right. Right? We can also have vertical reflections. Right? A vertical reflection is when the graph flips over the vertical axis. Right? Now, to the transformation algebraically, a vertical reflection means we're going to make that whole function negative. We're going to make the we're going to I think I might have said that backward. A vertical reflection. A vertical reflection is when we reflect it over the x-axis. So we're making that whole function negative. So all the positive y's become negative, and all the negative y's become positive. Right? So let's see. Let's look at an example of a vertical reflection. Here's one we can use. Well, we can stick with the quadratic function for that. All right. So if f of x is equal to x squared, graphically, that's going to look like this. Okay. Now, if we want to reflect that vertically, what we're doing is we're going to reflect it over that x-axis. So the entire function is going to become negative. Here, we'll make it red. So g of x, if that was equal to negative x squared, like this, right? The whole function, whatever it is becoming negative. We're going to reflect it across the x-axis. I like to think about it this way. All the y coordinates that were positive become negative, or vice versa. So our new graph then is going to look like this. It's a vertical reflection. Okay. Now we can have horizontal reflections as well. With a horizontal reflection, what we're going to do is just make all the inputs negative, right? So how I remember that, a reflection about the y-axis, how I remember that is I'm thinking, oh, all the positive x's become negative, negative x's become positive, right? So, x squared, when we reflect the quadratic toolkit function, nothing changes, so let's make a different one. Let's work with, how about the square root function, right? So if f of x is equal to the square root of x from toolkit functions, right? For these, I told you we have to learn all of these when we're dealing with this guy here. So that's going to graphically, that's going to look like this. Okay, there's our f of x equals the square root of x. Okay, now if I want to make a horizontal reflection, or reflect that across the y-axis, there's this teal one for that, I'll have g of x. I just want to make the inputs, all the inputs negative, or all the x's negative, so it's going to be the square root of negative x. Okay, so all these positive x coordinates, the points on the graph over here become negative, and that reflection It's going to look like this. Right? So there's a horizontal reflection. I'm sorry. Yeah, horizontal. I keep saying my word backwards today. All right. All right, so those are 4 basic transformations. There are 2 more that I want to talk about, but let's look at these 4 a little bit more deeply. All right, take a look at these examples here. So let's come back to that quadratic function from the toolkit functions. All right, how would the graph of this function change to match these new functions that are listed here? Or in other words, what transformation is going on in that formula? Right? So if we look at g of x equals negative x squared, right? It's not the negative of x being squared, it's the negative of x squared, right? So we've got a reflection happening there, right? We've got a reflection happening there, and that's where the whole function becomes negative, so that's going to be a vertical reflection, right? That's going to be a vertical reflection, or we might say this, we might say reflect across the horizontal axis, or the x-axis. Okay? When we look at this next example, what's happening here? We're just adding some constant out to the end. Okay, when we add some constant out to the end, that's going to be a vertical shift, right? If we match the pattern here, look, it's the function plus k, some constant, right? Since the constant is positive, the reflection the transformation that's occurring here is to shift up 3 units, right? Since we're adding the positive 3. All right, look at m of x. What's happening there? What transformation is happening there, right? Well, in this example, we're adding 3 to the input, right? It's this whole quantity, x plus 3 squared. So that means that's going to be a horizontal shift. It's counterintuitive. The positive, when we add a constant to the input, we're going left, right? So what's happening here, left correct, I should say. What's happening here then is we are shifting left 3 units. Okay, with n of x, oh, look, there's 2 transformations going on. First, let's look at what's happening here. Well, we're subtracting from the input, or subtracting from the x. So there's 2 things going on. First, we're shifting right 2 units. Because we're subtracting 2 from the input. That's a shift right 2 units. Okay, but then we've also got this constant at the end. It's negative. So secondly, what we're going to do then is we're going to shift down 1 unit. That's a W. Okay. One more. This one's got 3 transformations. Take a look at what's going on here. All right, we're doing a horizontal shift because we're adding 1, but look at the x is also negative. So that means we're doing a reflection as well. We're reflecting, all the x's that were negative become positive, so we're reflecting across the y-axis. And then lastly, out at the end, we're adding 5. So this has 3 transformations going on. 3. Right? So what's happening here? Well, let's see. We've got a reflect across the y-axis. We have a shift right 1 unit. And then lastly, we've got to shift up 5 units. All right, some examples of transformations as they appear algebraically in the equation. All right. Okay. So I mentioned there were 2 more transformations we were going to look at, 2 more transformations. The vertical stretch or compression and then the horizontal stretch or compression. All right, so what is this doing? This is like a vertical stretch or compression. It's like taking your graph and then just stretching it vertically or squishing it down vertically. Okay, how does that happen? Well, we've got to multiply our entire function or multiply all the y coordinates on the graph by some constant, right? If that constant is greater than 1, the graph is going to be stretched out. If that constant is between 0 and 1, that graph is going to be shrunk down, right? If it's negative, then there's two things going on. We've got a reflection with a stretch or compression. All right, so let's see. Let's look at an example. Should we use the x squared? I guess that one's good enough. Let's stay with that cubic parent function. F of x equals x squared. All right, so that's going to look like this. Okay, there's f of x equals x squared. Now, if I want to stretch that graph out, right, stretch that graph out, let's see, we'll call that g of x. Okay, if I want to stretch that graph out, I'm just going to say it's, let's just say, if I want to, let's call it 2x squared, right? That's going to, that's saying multiply all the outputs of this function, or multiply this whole function by 2, right? So that's a vertical stretch by 2. Okay, so how would that look graphically? Well, all of the y coordinates of any of my points are going to get multiplied by 2. Right, well, the y coordinate here is 0. When I multiply 0 by 2, I still have 0. Okay? But here, the coordinates of this point are 1, 1. The y coordinate is 1. When I multiply 1 by 2, I end up at that point there. Okay? This guy, the coordinates of this point are 2, 4. So when I multiply 4 by 2, I end up way up there. Okay? And then I would do the same over here with these negatives. So the vertical stretch of the quadratic toolkit function by 2 units is going to end up looking like that. Now you got to be a little bit careful with these vertical stretches because it also can look like a horizontal shrink. The only way to know exactly what's going on is to actually look at the values of the coordinates of these points and see what's happening to them. Okay, we can also squish this down, right? If we want to, let's say that f of x is going to equal 1/2 x squared. Okay, so what that's going to do, that's going to be a vertical compression, or I say shrink sometimes, same thing, vertical compression by 1/2. Okay, vertical compression by 1/2. So what that's, to graph that, I'm going to take the y coordinates of all the points on this graph and cut them in half. Right? So the y coordinate here is 1, half of 1 is 1/2. That point will be there. Half of 0, of course, it's just 0 still, right? Half of 4 is 2. That's going to go there. And then, you know, I could do some more. You know, I know they won't show up. Anyway, this guy, he's going to look like this. Let me put some things on the other side to make this better. There. Okay, so that teal or green colored graph, probably shouldn't have called him the same thing. Let's call him h of x. Okay, h of x. So with these vertical stretches and compressions, visually they can look like a horizontal stretch or compression. And sometimes they can be written algebraically either way. You just have to be a little bit careful with them. Let's take a look more closely at the horizontal stretch or compression. All right, with this guy, what's happening here? Well, here we're multiplying the input, or we're multiplying the x by some constant, okay? If this constant, And these are counterintuitive. These horizontal stretches are counterintuitive, just like the horizontal shifts are. If this constant is greater than 1, what we're actually doing is compressing the graph horizontally by 1 over k. And if that constant is between 0 and 1, what we're actually doing is stretching that graph by 1 over k. Right? Stretching that graph. That's a typo. I think that should say k. All right. If k is negative, of course, then we have two transformations going on. Two transformations going on. We're reflecting and stretching or compressing horizontally. So let's take a look at an example of that. Let's see. I guess we'll stick with the quadratic function. It's been working nicely. Okay, so that toolkit function, let's sketch that on here. Sketch that perfectly, but good enough. All right, and so if I want to do a, let's do red. Let's say, we'll say g of x. G of x is going to be 1/2 x, and then all of it getting squared. All right, so all I'm doing here is I'm taking half of my input. Okay, notice that it's inside the parentheses. Okay, so if I'm doing that, what am I doing here? Am I doing a horizontal stretch or a horizontal compression? It's horizontal because it's happening to the x, right? Inside there, it's happening to the input. Well, let's see. If that constant is between 0 and 1, which it is, 1/2, that means I'm stretching by that, oh yeah, I see, that really wasn't a typo. It should be by 1 over k. But what I'm doing here is I'm stretching by 2. Let's write that down. Stretch by 2. It's a horizontal stretch by 2. Of course, we're doing horizontals. Okay, so I'm going to multiply all my x coordinates by 2. Okay, so 0 times 2 is 0, that stays. But look, 1 times 2 is 2. 2 times 2 is 4. That's going to look like that. Let's see. Here. And here. Here we go. So I'm doing a horizontal stretch by 2 when I multiply the input by 1/2. Okay, I was wanting to correct that over here, but actually the way it's typed, it was correct the first time. I'm stretching by 1 over k when k is 1/2, right? When k is 1/2, 1 over 1/2 is 2. 1 over 1/2 is 2. All right, so, and I can also do a horizontal compression, and we'll do that one in how about blue? So say h of x is equal to 2x squared. This is saying I'm doing a horizontal compression by 1/2, right? Because it's 1 over the k. The k is 2, right? By 1/2. So that means that all my x coordinates of any points are going to get cut in half, right? So here, the x coordinate is 1, cut in half, it's 1/2. Here the x coordinate is 2, cut in half, that's 1. If it's a 3, it'd be 1.5. It's not going to show up on the graph, so I'll just do this much. Okay, so a horizontal compression is when we multiply the input by a number that's greater than 1. They're greater than 1, right? So look at, they look similar, don't they? They're not exact, so we have to be careful. We don't want to just visually look at a graph and decide what's going on. You've got to actually investigate the values, right? You've got to investigate the x and y coordinates and what change is happening in the x and y coordinates to determine if we're doing a horizontal stretch or compression or if we're doing a vertical stretch or compression. All right. Let's see, I just don't really need that. All right, let's look at transformations of functions from a little bit different perspective. You know, functions can be represented all different ways. We can represent a function by its formula algebraically. We can represent them by its graph. That's what we were just looking at. We can also represent a function by a table of values. By a table of values. Say this is a function here, f of x, right? When the input is -2, the output is 3. When the input is -1, the output is 5. Input of 0, output of 4. 1 results in 0, and 2 results in -2. Okay, so there's a table, right, with some inputs and some outputs of some function, f of x. Now, if I wanted to create a table of g of x, and g of x is defined as the negative of f of x, there's a transformation on that, right? That's going to be what? That's going to be a reflection across the x-axis, right? Or a vertical reflection, a reflection across the x-axis. So the whole function becomes negative, or f of x is really function notation for the y, for the output, right? For the output. So how is that table of values going to look? Well, if x is -2, right? Before the transformation, f of x was 3. Well, here, the f of x is going to become negative, so g of x would then be -3. Okay? When x is -1, g of x is going to be -5. When x is 0, g of x is going to be -4. When x is 1, g of x is, well, the negative of 0 is still 0, right? So that's going to stay. And when x is 2, g of x is going to be the negative of -2 or +2. Okay, so I don't need the graph. I can just apply the transformation algebraically. Here, h of x is 2 times f of x. What transformation is this? I've got a vertical stretch by 2. Right? Another way to think about this is all the y coordinates of points on the graph are being doubled, are being multiplied by 2. Or the entire function is being multiplied by 2. Right? So here's my table of values. If x is -2, what would h of x be? It's going to be 2 times f of x, right? Well, f of x, when x is -2, is 3. So 2 times 3 is 6. Right? When x is -1, 2 times 5 is 10. When x is 0, 2 times 4 is 8. When x is 1, 2 times 0 is still 0. And when x is 2, 2 times -2 is -4. All right. Look at m of x. Here, all of the inputs get split in half. Oh, this is interesting, isn't it? All the inputs. How are we going to, so I can't necessarily just copy down the x's. How am I going to make this table? How am I going to make this table? We have to think about it a little bit, right? Well, here we've got a horizontal stretch by 2. Horizontal stretch by 2. 1 over 1/2 is 2, right? Might even make a note because these can get a little bit confusing. Horizontal stretch by 2. All right. So what x is and what m of x is am I going to have? Well, let's see. If x is 2, 1/2 of x is -1, right? Is -1. 1/2 of x is -1. So if x is -2, 1/2 of it is -1, and f of x for -1 is 5. So m of x then is going to be 5. Make sense? Horizontal stretch by 2. let's see, if x is negative 1, well, half of that is negative 0.5, and I don't know an f of x for that. So I'm going to skip that value. How about 0? Half of 0 is still 0. So m of x must still just be 4 then. Okay? How about 1? Half of that is 0.5. I'm not going to know that value, so I'll skip that guy. How about 2? Half of 2 is 1. Right? So when x is 2, half of that is 1. So m of x is going to have to be 0. Can I finish that table? Well, I'll have to use some different x's, right? Well, they're a little out of order, but what if x were negative 4? Half of negative 4 is negative 2, right? So that means the f of x is going to be 3. Okay, what about 4? Half of 4 is 2, so that means m of x is going to be negative 2, right? How about this one, n of x? This is the horizontal stretch of f of x by 2, but then we're shifting it up 2. Well, the easiest way to do that is just to take a look at the values I found up here for m of x and then add 2 to each of them, right? So if x is negative 2, n of x is going to be 5 plus 2, or 7. All right, when x is 0, n of x is 4 plus 2, or 6. Okay, when x is 2, m of x is 0 plus 2, or 2. Okay, when x is negative 4, n of x is going to be m of x plus 2, or 3 plus 2, right? That'd be 5. And 4, that's going to, when x is 4, n of x is going to be negative 2 plus 2, n of x then is going to be 0. I don't know about you, but these tables, I find that sometimes these tables can be confusing. You really just got to think about what's going on there. Not very intuitive. All right. Let's look at a few more examples. Here we've got some graphs. We've got some graphs. Say you want to write the equation for that graph. Well, where do we begin with this? Well, we start by looking at our toolkit functions or remembering our toolkit functions. What shape does this graph on the left here most closely resemble? Well, if I look at my toolkit functions, it looks like it most closely resembles the reciprocal shape. It's not quite the same, is it? Right? Without the transformation, let's see if I can sketch that in there with whatever color this one is. Without the transformation, it would look like this. Yeah. Maybe we'll do a little dotted line. Oops, this should go over there. And then there should be an arrow on it. Without the transformation, because it would keep going. Without the transformation, that function there that I just wrote is the reciprocal function, 1 over x. That's a reciprocal function. Now, the graph that we're actually looking at, though, is a little different, isn't it? It doesn't look like there's any stretching going on, does it? It doesn't look like there's any shifting going on. I think there's a reflection, though, isn't there? What reflection is taking place here? Are we reflecting across the y-axis, or are we reflecting across the x-axis? In this case, it could be either one, right? If our black line was g of x, right? If it were reflecting across the x-axis, so a vertical reflection, we would write that as negative 1 over x, right? That would be a vertical reflection, right? And reflecting across the x-axis. If it was reflecting horizontally, we'll call him h of x. If it were reflecting horizontally, it would be 1 over negative x, right? All the x's that were negative become positive, positive become negative. That would be a horizontal reflection. In this case, do you see that it doesn't matter? Both of these answers are correct. Because, of course, when I distribute the negative sign, it's either negative 1 over x or 1 over negative x, right? So algebraically, these two expressions are exactly the same. They're exactly the same. So either one of these answers would be the correct answer here. What about this one? Let's take a look at the toolkit functions. It looks like the square root function, doesn't it? It looks like the square root function. What would the square root function without any transformations look like, though? Let's draw that on there. Let's say f of x is just plain old square root of x with no transformations. Let's see what that looks like. Well, when x is 1, y is 1. When x is 4, y is 2. Okay, so without any transformations, or the toolkit, let's see if I can get that drawn on there. The toolkit function for the square root function looks like that. So we know that it's not exactly the toolkit function. It's some transformation of the toolkit function. Well, what's going on here? I might think that this was a horizontal stretch. I'm sorry, no, a horizontal shrink. No, stretch, horizontal stretch. I also might think that this was a vertical shrink. I gotta just investigate. It could be one or it could be the other. One or the other. Now, if I want to do a vertical compression, right, or shrink, I'd have to come up with a number that y changed from when it got from 2 to whatever that is, 4.2 or 1 or something like that, right? Oh, that's weird. I mean, I'm sorry, 2 to 1.2 or 1, you know, the y's. That looks like that's going to be a little challenging for me. 1 down to, I don't know what that is. It doesn't quite look like 0.5. Let me just take a look at this from a different perspective. Let's take a look at this as a horizontal stretch. What might change in the x-coordinate of a point as it goes from 1 to its corresponding point? Let's see. Let's call let me just write them down. The x and y coordinates of that point are here. The x and y coordinates of this point are 4, 2. Okay. Well, let's see. If I were doing a horizontal compression, okay, how could the x's change? Well, let's see. 3. The x would change from 1 to 3 when I went from here to here, right? 1 to 3. That would be multiplying. That would be like multiplying by 3 or 1/3 because horizontal is opposite. Okay. Let's see here to. Oh, it's not even going to show up. So how would I know? I'm going to guess. I'm just going to guess right now. G of x is equal to horizontal, so that would be the square root of 1/3 x. This is my guess. How will I know for sure? Well, I could try some different points and see if they work, right? Or I could just graph this little guy and see what he looks like in here. Let's try graphing it. Let's see. Y equals, oh, I got stuff in there. Let me clear all that out. And let me check my mode. Am I in? I'm good, I think. Make sure I haven't used this in a while. I'll make sure that I'm not doing something funky. Okay. Let's see what, let's just start by graphing square root of x. Okay, there's our toolkit function. And then let's also put on the same graph, let's go ahead and put the square root of 1/3 x. Yeah, let's do it this way. Of 1/3. Oops, not times. I'm going to have to use parentheses. Let's see. 1 divided by 3, so that's 1/3 x. Okay, let's see what happens. Now I'm looking at my graph. It's looking good so far, but I need to investigate some specific points to make sure that they match the points that I've identified on my graph. this point here has the coordinates 3, 1. So let me change my window just to blow it up a little bit. Let's see. I don't care about negative x's. They don't work here. So let me do my x minimum of 0. And I don't care about negative y, so I'll make the y minimum 0. And we'll still let the maximum stay 10, and we'll use a scale of 1. All right, let's just look at that for a minute. There's a little better view. There's a little better view of the two graphs. Right, our trace function can help us investigate very specific points. Very specific points. Okay, so I hit my trace button. It put me on the upper graph. So that's the toolkit function graph, right? Let's see what happens. Let's make sure everything's right. When x is 1, y should be 1. Let's go to 1, 1. I'm just moving left. X is 1. Y is 1. Yeah, that's about right there. How about when x is 4? That one might show up better. When x is 4, y should be 2. Getting over there to x equals, oops, I went too far. When x is 4. It looks about right. Okay, let's do this. Let's look at the table of data values on there. We can see them better here, can't we? There's x was 4, y is 1. It's not quite exactly right. I wonder what's going on with that. Am I on the right graph? Oh, so I may have discovered something here. Let's go on that lower graph and see what happens. Maybe this isn't quite correct. Let's go to that lower graph and see what happens. Back to there. Let's do a trace and get down to that graph. Let's look at the table here. Oops. Let's look at the table on that lower graph. All right, let's find an x that we want to see. We want to see, oh, let's see what happens when x is 1. Let's go all the way up to 1. 1 and 0.5. That's about right. Let's see what happens when x is 3. Go down to 3 and look at that. Y is 1. That's exact. So I think I'm in a pretty good place here. I think I've got the right values. I think that square root of 1/3 x matches. And I could check a few other points if I wanted to too. All right? So that first graph was weird though, wasn't it? Let me look at that table one more time on that first graph. Oh, we're not on the right one. Trace. Let's get up there to that top graph. Okay. Trace and table. Oh, it's not going. Wait a minute. Okay. Yeah, that's all right. Okay. All right, let's look at a few more. Got this guy and this guy. What's happening here? We'll go back to the toolkits. What does this graph shape most closely resemble? Absolute value, doesn't it? Definitely got a reflection going on, right? Also, I think I got a shift up, right? I've got a reflection and a shift up. Let's just put that toolkit function on there so we can see it visually. Here's what the toolkit function looks like for the absolute value function. Put some arrows to indicate that that goes on. That's f of x equals the absolute value of x. All right. Now what's going on with our graph that we're looking at here? Well, I definitely have a reflection, right? I got a vertical reflection. That's getting flipped over the horizontal axis. So if I'm writing g of x, I definitely have a negative going on. What else might? I'll put my stuff down there. What else might be going on? Looks like I've got a shift up. Look, this point clearly corresponds to this point. It's going up 2 units. So I got a +2. Now I just have to determine, well, do I have any vertical, horizontal shifts or reflections? Do I have any? Well, what I want to try to do is I want to pick a point. I can assume looks like there aren't. No, it does look like there's something going on. So let me just say, let me see if I can write this with a vertical stretch. So let me just assume there's something vertically going on. Let me just stick an A in there. Okay, let me stick an A in there. And let me just assume there's no horizontal right now, just a vertical stretch or compression. How would I know for sure or algebraically? Well, I want to pick a point that's on my graph that I'm interested in, a very clear point where I can see the X and Y coordinate clearly. How about this one? I'm just randomly choosing it because it's a whole number point that I can very clearly see. X is 2, Y is negative 2. Okay? What I'm going to do is plug those values in and solve for A. Right? So let's see, if y is negative 2, g of x is our function notation for our y. So we're going to say negative 2 equals negative a times the absolute value, here the x is 2, right, plus 2. And I'm going to go ahead and solve for that a. Right, I want to go ahead and solve for that a to see if I've got some kind of vertical stretch or shrink going on. Well, if we subtract 2 from both sides, what do we have here? 0 equals negative a times the absolute value of 2. Well, that's really hard to solve, so I might not have chosen the best point, did I? Let's pick a different one. How about this one? How about 1, 0? All right, so that one wasn't definitive. Let's try 1, 0. So I'll put a piece of paper down under here. Move this up a little bit. Y is 0 times negative a times the absolute value of x, 1, plus 2. All right, subtract that 2 from both sides. So then, just right up here, so it'll show on the screen, negative 2 equals negative a times the absolute value of 1, which is of course just 1, right? Just 1. So if negative 2 is negative a has to be 2. So it looks like I have a vertical stretch by 2, doesn't it? So I think my g of x here then is going to be negative 2 times the absolute value of x plus 2. And I can test that. I can put that in my calculator, look at it there, right? Or I can just sort of say, well, if this was correct, this means all my x coordinates would be multiplied by 2 after the reflection, and test it all that way. All right, one more. So we've got parabola, right? So we know the toolkit function there is the quadratic function. We know that. So let's see if we can put that on there. The quadratic function, that's normally going to sit right there on the origin and go something like this. And go something like that, right? Well, I can see a coordinating point, the vertex of this parabola. It looks like that's some shifting going, shift righting and shift down. I don't know about that vertical stretch or horizontal stretch or anything about that. Well, let me just write what I have so far, what I can see visually so far for my g of x, all right? Well, what I can visually see is some shifting, all right? So I got my x squared. I'm going to put him there. Now I've got some shifting, actually. I'm going to make room for my shift. Okay, I've got a horizontal shift right, 1, 2, 3 units, right? Because I can see the vertex to the vertex, right? Shift right 3 units. So that means I would have to subtract 3 from the x. Remember, our horizontal shifts are counterintuitive. But I've also got this vertical shift going down 2 units, right? Move down 2 to get from here to here. So that's going to be a minus 2. Now, what I don't know for sure, just on visual inspection, is there any horizontal stretch and shrink, vertical stretch or shrink? With this one, as with this one, either the horizontal or the vertical, I could write it either way, with either a horizontal stretch and shrink or a vertical. So I'm going to choose a vertical. Let me just choose an A to represent my vertical stretch or shrink, and let's just see if that will work for us. So I want to pick a clear point and substitute those values in and solve for A. Well, a clear point on my graph, it looks like this one might work. Okay, let's see. And the coordinates of that point are 4, -1. So there's my x and y. Let's substitute them in. All right, so -1 then equals A times x, that was the 4, minus 3, 4 minus 3 squared minus the 2. All right, so if I solve for A here, 4 minus 3 is just 1. I'll add the 2 to both sides. So then 1 equals 4 minus 3, that's 1 squared, A times 1. So A is clearly going to be just 1 here. So I do not have any stretching or shrinking going on. I just took that graph, shifted it right, and moved it down. Okay. So again, the way to deal with these, I'm very visual. So I like to sketch them so that I can kind of see. It helps me not to make mistakes. The horizontal stretch and compression, the vertical stretch and compression can be tricky. To determine that one, you just pick a clear point. Substitute that into the equation that you can see visually, and then solve. All right. A little bit more here. And one more topic is kind of lumped in here into this section 1.5 with the transformations, and that's the concept of an even or an odd function. Okay, an even function is one that when you substitute -x in for all the x's, it turns out to be the same function after you simplify. So f of x equals f of -x. When we graph even functions, they are symmetric about the vertical axis. What does it mean? It means when you flip them over the vertical axis, they look exactly the same. The perfect example of an even function is the quadratic function. Flip that parabola and it looks like over the x-axis, over the y-axis, and it looks exactly the same. Okay? An odd function is one where f of x equals -f of -x. What does this mean? This means substitute all the x's in with a -x, simplify, and you should get the exact negative of the original function. Okay? When you graph odd functions, they are symmetric about the origin. What does that mean? That means, think about an old-fashioned board game spinner. If something is symmetric about the origin, if you spin it 180 degrees around the origin, it's going to be exactly the same. Right? The perfect example of the odd function is the toolkit cubic function. Right? Toolkit cubic function. Imagine spinning that graph 180 degrees. It's going to look exactly the same. Okay? And f of -x is going to be what? It's going to be the negative x cubed, or the negative of x cubed. Right? So it's exactly the negative of the function. All right? And of course it is possible that a function can be neither even nor odd. It doesn't have to be an even or an odd function, because it may not have either one of those, the graph may not have either one of those symmetries about it. Or neither one of these two rules may apply. All right, let's look at some examples. Let's see if we can determine that these functions listed here are even, odd, or neither. Well, I don't have the graph. I could put it in a calculator or put it in Desmos online and look at it. But it's easier if I just use the algebraic rule, right? So even, I just write it up here. Even means that f of x equals f of -x. And odd means that f of x equals -f of -x. Yeah, that's right. So how are we going to figure that out? Well, let's find out what f of -x is. That's going to help us quite a bit. If we just substitute a -x in there, and see what we've got, if it ends up with the same function after we simplify, and it's going to be even. If it isn't, if it's the opposite of the same function, then it's going to be odd. And if it isn't either one of those, it's neither. Well, what is f of negative x here? Let's see what it is. F of negative x is going to be negative x squared plus 3, just substituting a negative x in there, right? When I simplify that, negative x squared is the same as x squared, isn't it? It just simplifies to x squared plus 3. Since those are the same exact function, right? They're equal. I know that this is an even function. F of x is an even function. How about g of x? Substitute a negative x in there. Find out what g of negative x is, right? That's going to be negative x cubed minus negative x squared. All right, let's simplify. Negative x cubed, that's a negative x times a negative x times a negative x. So that's going to be the same as negative x cubed minus negative x quantity squared. That's negative x times negative x. It's the same as positive x squared. All right? So is this function here the same as this function here? No. They are not, because look, that's a positive x cubed. Is this function here the opposite of this function here? No. The opposite of this function, right? Let's write that. Let's put that in a different color. Negative g of negative x, that'd be the opposite. I did that wrong. Negative g of x is going to be what? Negative x cubed minus or plus x squared. Right? That doesn't match either one. So that's going to be a neither. Another way to think about these odd functions is in the is that I could say yeah, that's fine. I could also say, let me just say that f of negative x. Yeah, I'll leave it like that. Okay, so look at this guy. The cubed root of x. Well, let's see, what is h of negative x? That's the cubed root of negative x. Is the cubed root of negative x, how does that simplify? Would it be the negative of cubed root of x? Can I say this? Does it work the same as when we're cubing things? Well, let's test it out. Let's see. What is the cubed root of negative 27? Well, it's negative 3, right? I can take up my calculator if I'm not sure. Let's put the cubed root of negative 27. So that's going to be negative 27 raised to the 1/3 power, right? That's how we do a cubed root. Negative 3. So what is negative the cubed root of 27? Well, 27 raised to the 1/3 power. It's 3, and so negative 27 raised to the 1/3 power is negative 3, right? So that's going to be equal to, they are equal. They are equal. So here we can say that h of negative x equals negative h of x. That's the other way that I like to think about that. So I can say that this is an odd function. Let me write that. I was trying to write that and I thought it'd be confusing, but I think it's not. So we would say f of negative x equals f of x. Negative f of x, sorry. There we go. F of negative x equals negative f of x. One more. P of x, 4 over x plus 5x. Let's see what p of negative x is. 4 over negative x plus 5 times negative x. Let's simplify that a little bit. We could call that negative of 4 over x, right, if I pull that negative out. and then plus 5 times negative x, we could say that's negative 5x, couldn't we? Well, what is the negative of p of x? What is that? Well, it's negative of 4 over x plus 5x. When I distribute that negative sign, it's negative 4 over x minus 5x. Look, they're the same. So this one, I would have to say, is an even function. Oh, no, not the same. They're the negative. Here, we're saying p of x equals negative p of x. So this, again, is an odd function. Okay, odd function. Again, if we substitute all the negative numbers in and you have the same function, f of x equals f of negative x, then you have an even function. Odd function, you could think about it two ways. This way is actually a little confusing. It's how your textbook says it. For me, I like to think about it this way. If f of negative x equals negative f of x, right, then it's odd. Neither one of these cases exist. You know that it's neither. All right, that ends the lecture for section 1.5.